Okay. Under what circumstances do we have uniform acceleration? Well, uniform acceleration, of course, results if we have a constant net force on a constant mass. Now, the mass might not be constant, and in that case, we have to have a net force that's always proportional to the changing mass, always in the same proportion to the changing mass. That is, if the mass doubles, the force is going to have to double. If the mass is cut in half, the force is going to have to be cut in half. Force is proportional to changing mass, and that'll give us uniform acceleration. Usually when we have changing mass situations, acceleration is not going to be uniform. Definition of average velocity. Okay, but what we're trying to do is work out our ideas and formulate our ideas of uniformly accelerated motion. Definition of average velocity is, well, delta S over delta T is going to be the average of the two, the initial and the final velocity when acceleration is uniform. Multiply both sides by delta T and we get this equation. Definition of acceleration is that acceleration is delta V over delta T. If acceleration is uniform, then if we multiply acceleration by delta T, well, if we take our delta V over delta T, which is Vf minus V naught over delta T, set it equal to acceleration, solve for Vf, we get this equation. Then we can eliminate from these system of two equations, we eliminate delta T, say solve this one for delta T and plug it in here, or solve this one for delta T and plug it in here, it doesn't matter. We're going to get this equation, Vf squared equals V naught squared plus 2a delta S, and this equation is obtained by eliminating Vf. Just take this expression for Vf and substitute it here and do a little algebra, and you get this. And these are the four equations in terms of which we formulate uniformly accelerated motion. Okay, what's our basic set of premises? Our basic premise in dealing with projectile motion? Well, our basic premise is that the projectile is falling. Okay, you got a projectile, you projected it, falls freely to the ground, being accelerated by or under the influence of only the force of gravity. Now that's not really true. When we toss something in the vicinity of the Earth, we almost always have air, especially if we toss it for any distance. We can always evacuate a bell jar and attempt to launch a projectile inside the bell jar, but that's not even very interesting. We actually I don't know anybody that does that. In any case, if the only force is gravity, and that's our first approximation, and it's a good approximation as long as we have small velocity and relatively dense masses being used as projectiles, then the acceleration in the vertical direction is g, and the acceleration in the horizontal direction is 0. Obviously gravity is going to act straight down in the context, in the reference frames from which we consider projectiles, and doesn't have any force in this direction. If we ignore air resistance and any other non-gravitational forces, then there's 0 acceleration in the horizontal direction. And as a result, we choose our x-y coordinates so that y is vertical and x is horizontal. In that case, we see that the y acceleration is negative g, and when we put the x-y axes on it, we usually put y upward, not downward. You can put it downward if you want, but I'm going to stay with the convention that y is upward here. So acceleration is negative g, and the x acceleration is 0. And the other main premise is that the x and y motions are independent except for delta t. So that we analyze our y motion, we analyze our x motion, both independently. The only thing they share is delta t. A typical calculation is to calculate the time of fall, the delta t of fall, and then plug that in for with the initial x velocity to get the range of a projectile. Okay, what about the forces on a pendulum? Why does pendulum undergo simple harmonic motion? Well, a pendulum And when I say a pendulum, I'm really meaning a simple pendulum, and I kind of use that carelessly. I really should say a simple pendulum, but a simple pendulum consists of a string or cable of negligible mass, and then a mass at the end of the pendulum, and it's really supposed to be a point mass at the end of a pendulum. Spherical mass, where the point is considered to be the center of gravity, is of course the typical simple pendulum, okay, the canonical simple pendulum or whatever. Now, what forces act on this system? Well, you have mg, the weight of the object, of course, and then you have the tension along the string. Well, if we have a small angle, and this is what we do when we talk about pendulums is almost always, at least at first, a small angle approximation, then the tension is approximately equal to the weight. That's because the vertical component of the tension, of course, has to be equal and opposite to the weight. For small angles, we have very little vertical motion, so we approximately have vertical equilibrium. And if we make that approximation that we have vertical equilibrium, then the y component, or the upward component of the tension, is equal to mg. But for small angles, the upward component and the actual tension are almost indistinguishable, so that the tension is approximately mg. The x force, the Tx, is the net force in the pendulum. It's the net result of this force and this force. These forces can't be in equilibrium. They're in y equilibrium, but there's an x component, and that will be our net force. And by proportionality with the geometry of the situation, we can see that the ratio of Tx to T is the same as the ratio of x to L, except that, of course, Tx is in the negative direction when x is positive, so we put a minus sign here. And from that, we conclude that Tx is a negative of mg over L times x, multiply through by the tension, and the tension is mg, which tells us that our net force is negative mg over L times x, which is of the form negative kx, with k equal to mg over L. And this implies that we have then simple harmonic motion with omega equal to the square root of k over m, which reduces here to the square root of g over L.